like to travel to the Moon, Mars, or other destinations in space? Since 1961, humans have been traveling to space. However, the farthest anyone has ever gone has been to our Moon. If we are to explore farther out into our solar system, we'll need a spacecraft that can do more than we've ever imagined.
And liftoff at dawn, the dawn of Orion.
In December of 2014, NASA completed a test launch of NASA's new Orion spacecraft. Orion traveled 3,600 miles above Earth. That's 15 times farther away from the planet than the International Space Station. For this test flight, no astronauts were on board. The spacecraft's computers controlled the flight and collected data from launch to landing. Scientists are now studying this data and conducting more testing to better understand some of the hazards or safety concerns that astronauts and the spacecraft could encounter during long-distance space missions. As an engineer who works on Orion, I'm so excited about the new opportunities that this spacecraft will give us in traveling farther into our solar system and discovering the unknown. Now here's NASA astronaut and engineer Stephanie Wilson to tell you about the challenge.
Hi, I am Stephanie Wilson. I am so excited that you've accepted the challenge to be part of NASA's team. NASA is developing the next generation of space exploration vehicles. Let us explore one vehicle known as Orion. Orion will be able to transport humans beyond low Earth orbit, traveling to the Moon, Mars, and other destinations in space. Your team's challenge: design and build your own model spacecraft for testing. Your spacecraft must be built to protect a crew of astronauts during orbit. As you test and improve your design using the engineering design process, you may face problems. You may have to come up with new solutions, but you will be building the skills and knowledge to help solve tomorrow's challenges in space. Since Orion will take my colleagues and I into space, I cannot wait to see the spacecraft you create.
Thanks, Stephanie. Now that you have your assignment, it's time to get to work. Your spacecraft must carry 2 astronauts safely. Each astronaut is 3 to 7 centimeters tall. Each student team must design and build secure seats for both astronauts. The astronauts should stay in their seats during each drop test without being glued or taped into place. Have one hatch that opens and closes and is sized so the astronauts can enter or exit easily. The hatch should remain closed during all drop tests. Fit within the simulated rocket. This item serves simply as a size constraint, and the spacecraft will not be stored in or launched from this item. Must include an internal holding tank for fuel with a volume of 30 cubic centimeters. And finally, the total mass of your spacecraft cannot exceed 100 grams. Now it's your turn. Be creative with your designs. I can't wait to see what your teams come up with.
You are the future scientists and engineers who will help us improve human space exploration, and I am so thrilled to have you as part of our team. Together, we'll chart a path to new discoveries, and who knows, you may even use Orion one day to become one of the first astronauts to set foot on Mars. Good luck, and we look forward to seeing your solutions.
explore farther out into our solar system, we'll need a spacecraft that can do more than we've ever imagined.
And liftoff at dawn, the dawn of
In
Orion.
December of 2014, NASA completed a test launch of NASA's new Orion spacecraft. Orion traveled 3,600 miles above Earth. That's 15 times farther away from the planet than the International Space Station. For this test flight, no astronauts were on board. The spacecraft's computers controlled the flight and collected data from launch to landing. Scientists are now studying this data and conducting more testing to better understand some of the hazards or safety concerns that astronauts and the spacecraft could encounter during long-distance space missions. As an engineer who works on Orion, I'm so excited about the new opportunities that this spacecraft will give us in traveling farther into our solar system and discovering the unknown. Now here's NASA astronaut and engineer Stephanie Wilson to tell you about the challenge.
Hi, I am Stephanie Wilson. I am so excited to be accepting the challenge to be part of NASA's team. NASA is developing the next generation of space exploration. Let us explore one vehicle known as Orion. Orion will be able to transport humans beyond Earth, traveling to the moon, Mars, and other destinations in space. Your team's challenge. Design and build your own model spacecraft for NASA. Your spacecraft must be built to protect the crew, astronauts, and their family. As you test and improve the design using the engineering design process, your space project, you will have to develop new safety. If you will be building the skills and knowledge of myself and my challenges in space. Since Orion will take my colleagues and I into space, I cannot wait to see the spacecraft you create.
Thanks, Stephanie. Now that you have your assignment, it's time to get to work. Your spacecraft must carry 2 astronauts safely. Each astronaut is 3 to 7 centimeters tall. Each student team must design and build secure seats for both astronauts. The astronauts should stay in their seats during each drum test without being glued or taped into place. Have one hatch that opens and closes and is sized so the astronauts can enter or exit easily. The hatch should remain closed during all drop tests. Fit within the simulated rocket. This item serves simply as a size constraint, and the spacecraft will not be stored in or launched from this item. Must include an internal holding tank for fuel with a volume of 30 cubic centimeters. And finally, consider the mass of your spacecraft will not exceed 100 grams. Now it's your turn. Be creative with your design. I can't wait to see what you come up with.
You are the future scientists and engineers who will help us improve human spaceflight. And I am so thrilled to have you as part of my team. Together, we'll chart a path to
guys need to be quiet. Okay, got it.
We're doing it.
Pretty much anything that you can observe on the land, both sometimes even in the ocean. Very exciting. Enormous amount of science and the
Every 12 days, we will map the land masses, and then we can take those mappings and we can compare them. We can do what we call interferometry.
where we can take an image acquired on one day and combine it with an image acquired 12 days later from that same vantage point, looking at the same point on the ground. And when we do that, we can see the motion of the ground down to a fraction of the radar wavelength, which in this case is on the order of a few millimeters.
NISAR, it has two radars on it, two synthetic aperture radars. One is an L-band and the other is an S-band.
So it's kind of the Tesla or the Maserati of radars, whichever you think is called.
This here is the radar payload. That is the spacecraft bus. Large 12-meter reflector, common antenna system for both L-band and S-band to send out the RF signal and capture the return signal.
Good morning, Paul.
How are you today?
Yeah, I'm fine.
The pandemic is something that we were not counting on when we developed this project.
The NISAR project was actually pretty well versed with this remote operations because of the Indian engagement. It was a little bit of WebEx fatigue, but I think we're learning how to do it better now.
But yeah, we're all in great spirits, and we will take a little hit to the schedule, but we've been waiting a long time for this mission, and we want to do it right. We want the hardware to work, and we want the science to be done.
One of the best things we can do to increase diversity in the sciences is to make it easier for people to enter the sciences.
The data is going to be freely available to everybody. You aren't going to have to pay for it like we do with some satellites.
So making the data free, having it easy to download to your own machine, all of that stuff is critical if we want to remove those barriers to entry to the field.
I'm looking forward to the sense of discovery that I think we're going to have when NISAR data start coming down.
Earth science is incredibly important to understand what's going on in the name of what our children and grandchildren are going to have to face in the future. And all the information we collect now is only going to help them understand that better and hopefully make their life better.
Digital electronic subsystem, cognizant. You know, the radar will. I can't recall. There we go.
That's our real life here in 2020.
Development stimulated to the point where we will have something that we can use in spaceflight. We have a partner in this challenge, the Robert Wood Johnson Foundation. Their mission is to improve the health of communities, and so they want a particle instrument that has a lot of the same qualities that a spacecraft particle instrument would have.
We are focusing on building a much more robust culture of health in America. And that means working with all kinds of different people and partners. We saw NASA as one of those opportunities. And it actually turned out to be a pretty interesting fit with their own interests in looking for innovations that work on space and on the Earth.
For the ISS, it's like a can of air that's been there for 17 years. No fresh air. We need to have that small, robust, maintenance-free instrument to measure particles on the space station. And so we have that synergy between the Earth application and the space application, and that's combined in the Earth and Space Enterprise.
We had 20 proposals come in, and a panel of judges, including NASA and Foundation members, down selected that to 3. Those 3 finalists were each given $50,000 to build a prototype based on their proposal, based on their technology. Those 3 prototypes will be in our test chamber together, and we will go through a series of challenges where we're generating aerosols in the chamber.
Some of the things we had to keep in mind for sampling on the space station are a little different for what we would normally consider for sampling here.
There is a growing interest in understanding air quality at the community level, at the neighborhood level, at the level of the school. And there are a lot of great sensor devices out there today that can do so in a broad way and a cost-effective way.
I just returned from the World Health Organization First Ever Air Pollution Conference in Geneva, and they're looking at a lot of low-cost or lower-cost sensor solutions that, for the third world or for less affluent countries, cost is a significant factor. But what they're struggling with is that there's a lot of low-cost, low-quality sensors. So trying to identify low-cost but high-quality sensors, which is really what we're looking to do.
This challenge gives us the opportunity to have not just evolutionary aerosol technology, but revolutionary aerosol technology at our disposal at NASA. There's new things that you can't buy that are being developed in this challenge.
Our end goal is really to advance technology for area monitoring and personal monitoring so that we can understand more about people's exposures to aerosols and really make it possible to create a healthier environment for people on the space station and here on Earth.
We designed a new aerosol technology that can basically measure both particle and aerosol mass, size distribution, but also gives you kind of optical properties of aerosols. This is incredibly important because what we can do is we can take this data and really get a really deep understanding of air quality. So with our device, we built it in ways where it can be scalable and deployed across large networks, and then you can take this data and actually start understanding the sources and composition of different types of aerosols.
To me, what's really exciting is the fundamental underlying challenge of air pollution, and I think that it's great that NASA and the Robert Wood Johnson Foundation have teamed up to help find solutions to solve that problem.
My hope is that one or more of the finalists will be able to partner with NASA to do a technology demonstration on the International Space Station with their partners. The other thing I hope is that there would be a smart city application with one of these finalists or more, because there's all kinds of solutions that we need to monitor to improve our awareness of our surroundings. Smart city application, you can look online and find out how clean the air is and make your decisions based on that.
other worlds begins with this world, with understanding the evolving relationship between life and its environment. No one understood this better than Dick Holland. For the first 30 years of his career, mostly at Princeton University, Dick pioneered the study of Earth's atmosphere and oceans as evolving, coupled chemical systems. His approach was profound in its simplicity. As a theoretician, he did not pursue complex composition models. As an experimentalist, he was cautious about sophisticated techniques. As a field scientist, he did not organize large, complicated campaigns. Instead, Dick always sought the simplest path to the heart of even the most complex questions. Combining nearly encyclopedic knowledge with basic thermodynamic and mass balance concepts, Dick constructed logical arguments while others were often lost in equations. This doesn't necessarily prove anything to Dick's logical study, before proceeding to lay out an argument so elegant, so informed, and so logical that it might as well have been a geometry. Dick taught his style and perspective to a generation of scholars by writing 2 books that quickly became classics. These masterpieces put together a tremendous amount of information and original thinking to sketch out a working model of the Earth system and its evolution. In this way, Dick organized and defined many of the key questions that drive the field even today. People look at Earth, look for life beyond, the same way since. After moving to Harvard, Dick proceeded to spend most of the next 25 years trying to answer one of those key questions. What caused the increase in atmospheric oxygen halfway through Earth history? A transition that Dick dubbed the Great Oxidation Event. Unfortunately, he departed us before he could answer this elusive question. Dick left it as an exercise for his many students. We carry his legacy into the future.
Robert A. Ward died on Wednesday, September 19, 2012 in Rapid City, South Dakota. Bob had been diagnosed with cancer in 2011 and following treatment had been declared cancer-free. However, he died from complications resulting from the early 2012 treatments. Bob received his PhD in botany from Virginia Tech and his bachelor's and master's from Humboldt State University. In later years, he attended both the Harvard Institute of Educational Management and the Stanford Graduate School of Business. Bob's leadership and scientific career spanned several decades in the academic, federal service, and private sector. He was well known for his scientific investigations of the perennially ice-covered lakes of the McMurdo Dry Valleys and their use as analogs for Precambrian ecosystems on early Earth and as analogs for potential aquatic habitats on early Mars. In 1993, Bob was instrumental in organizing and leading the McMurdo Long-Term Ecological Research Project, a National Science Foundation-funded interdisciplinary and multidisciplinary study of the aquatic and terrestrial ecosystems in the ice-free regions of the McMurdo Dry Valleys. Bob served as a visiting senior scientist at NASA headquarters in Washington, D.C., providing programmatic support to NASA's exobiology, controlled ecological life support system, and biospherics programs, and contributing to many studies aimed at supporting the human exploration of Mars, such as the Strategic Exploration Initiative and the Augustine Report. While at the Desert Research Institute, Bob served as Vice President for Research and as a research professor. Bob served as the Executive Officer for the National Science Foundation's Office of Polar Programs. Following his time at the National Science Foundation, Bob served as Provost and Vice President for Academic Affairs at Idaho State University. In 2008, Bob became the 18th president of the South Dakota School of Mines and Technology, where he quickly embarked on a bold path to increase the university's stature as a world-class technological university. Having participated in 11 expeditions to the Antarctic, Bob was the recipient of the United States Antarctic Service Medal and served on the National Research Council's Polar Research Board. He was a fellow of the American Association for the Advancement of Science, the Royal Geographical Society, and the Explorers Club. Bob was a leader, an international polar research scientist, mentor, and above all, an explorer. His passion for climbing became the university president.
that there are three, not two, primary divisions of life: the eukarya, bacteria, and archaea. This classification scheme represents one of the 20th century's landmark achievements in science and has fundamentally changed our understanding of evolutionary biology. By basing his classification on the sequences of molecules involved in the cell's earliest machinery for expressing genes, rather than purely physiological characteristics, Rose opened up a new way to quantify evolution, a new window on the origin of life, and a scientifically rigorous way to identify and classify all organisms. This has been especially transformative in the case of life. The vast majority of which cannot be captured, but which represents the principal components of its development. Rose's motivation to initiate the sequencing project was to understand the very earliest phases of life, in an attempt to understand how the complexity of organisms evolved from much earlier stages. His abiding interest in evolution itself, and he personally regarded the discovery of the idea as a spin-off, albeit one that is credited only now to the Rose's work was an early forerunner of today's genomic biology, and many extensions to revolutionize biology, ecology, and agriculture. As many academics now classified as science awarded by the Royal Society. Doing that, the U.S. National Member of Science and the National Academy. His contribution to animal biology live on in his experimental discovery, his theoretical work on the genetic code, and his vision of the evolutionary process in action.
David McKay passed away on February 19, 2013 at age 76, ending a distinguished career in lunar science, meteoritics, and astrobiology. He played key roles in NASA's lunar exploration and astrobiology programs, understanding the lunar regolith and the processes operating in the near-lunar environment, developing ideas for utilization of planetary resources, examination of Martian meteorites for potential biogenic signatures, and the formation of NASA's astrobiology program. At the time of his death, he was Chief Scientist for Astrobiology and Planetary Science and Exploration at NASA's Johnson Space Center, Houston, Texas. He has been described as a pioneer among pioneers in the space program. David joined NASA's Manned Spacecraft Center in Houston in June 1965 to train astronauts to collect rocks on the moon. He was the only geologist present in mission control during the lunar landing in July 1969. To many in the scientific community, David is best known as the lead author of the 1996 science paper that presented evidence for ancient Martian life in the Allen Hills 84001 meteorite. The publication of the science paper created an explosion of excitement and criticism in equal measure. The excitement surrounding the possibility that Mars may have harbored ancient life led spacefaring nations of the world to reignite their Mars exploration programs. The establishment of the NASA Astrobiology Institute in 1998 was also in part a consequence of David's pioneering work on ALH 84001. David was married to Mary Fay for more than 40 years and was the father of 3 girls, Amy, Susie, and Jill. He was delighted to have 3 grandchildren. Dave was quiet and unassuming, had a sharp, humorous wit, and a genteel manner. His love of science inspired 2 of his daughters to complete their PhDs. He enjoyed traveling, particularly to Japan. We miss you and thank you, David, for your friendship and guidance over these many years. You have helped point the way to the moon and to Mars.
Planetary science and exploration were Tom's lifelong passions. Already at the tender age of 7, Tom's Northwestern Reserve University. In 1976, he joined the faculty in the Department of Physics at the University of Alabama at Birmingham, where he would teach astronomy to over 10,000 undergraduate students over the next 30 years. Combining his love of astronomy with interest in chemistry and geology, he explored space from his laboratory, studying the properties of stardust, meteorites, and geological samples, including what may be microfossils from the beginning of life on Earth. His diverse scientific portfolio also included topics ranging from stellar magnetic fields to the origin of the KT events that wiped out the dinosaurs, to the composition of interstellar dust and the mineralogy and astrobiology of the surface of Mars. He was very generous with his time in educating the public and was often seen, heard, or read on local TV, radio, and newspapers. Tom was nothing if not passionate, and he was especially so for planetary exploration. The highlight of his career was when he joined the Mars Exploration Rover team. He was on hand to send the control commands to the rover Spirit when it reached out its robotic arm to study the rock Adirondack. And thereby Tom fulfilled his childhood dream of touching another world. The MER team later honored Tom by naming a Martian rock formation, Dowiak Ridge, as a memorial to his contributions.
John Billingham was born in the United Kingdom and began his medical career in London in 1954. Thereafter, he served in the Royal Air Force until 1963, when he accepted a position as the head of environmental physiology at NASA's Manned Spaceflight Center in Houston, emigrating with his wife Margaret, later an eminent physician and pathologist in her own right. In 1965, he became chief of the biotechnology division at NASA AIM, where he became familiar with the center's work in exobiology, leading to a collaboration with Tony Oliver of Hewlett Packard. He co-directed the 1971 summer study to assess what would be required to mount a realistic effort aimed at detecting the existence of extraterrestrial intelligent life. Using Project Cyclops as a jumping-off point, JB, as the French knew him, became a lifelong advocate for SETI and the people who made it all possible, both formally and informally. He was a leader in a community of creative and dedicated people who shared a thirst for knowledge of life beyond Earth. He was proud to be known by the company he kept as himself. Surely he garnered official recognition for his efforts along the way. Unofficial recognition came in many satisfactory forms as well. JB kept distinguished company at work, but not more distinguished than at home. The talented and dedicated people who come from foreign lands to participate in the vision of space exploration is a lesson that NASA and the U.S. government should never forget. That John Billingham was among them, and that he shared the vision of the near future. The universe operating at the speed of light was and is to our great
Vishankari was best known for his studies of the formation of organic solids in the atmosphere of Titan. In a seminal paper in Icarus, Kari, together with Carl Sagan and others, determined the optical properties of solid organic material produced under simulated Titan conditions. They referred to the solid material as thorium. Kari and his team measured the indices of refraction of Titan thorium over a very broad range of wavelengths, from the microwave to the X-ray. Modelers quickly found that the optical properties were used to determine the reflection rate. The calculations made with these observations agreed well with telepathic spacecraft. This agreement between the laboratory technologists and the public was the basis for the growing acceptance of organic solids as the source of behavior in Titan. Kari also worked on organic production in other settings, including the atmospheres of the giant moons and the surfaces of icy rocky moons. Kari also worked in the field of nanotechnology, producing insight into samples of carbon nanotubes for analysis and experiments. Vishankari was born in Nashville, England, where he earned an undergraduate degree from Lawrence University. He came to the U.S. to complete his Syracuse. His formative work was done with Carl Sagan from London University. pleasure to work with him. He's enthusiastic about science and listened carefully to everyone, from students to senior scientists. And he listened to what they said and considered it equal, regardless of the source. He's missed.
His management style was characterized by a fierce loyalty to the Institute's employees and an easy willingness to let them try new ideas. During his tenure, Tom led more than $250 million of federally funded research and raised more than $90 million in private funding for SETI research. For distinguished service to NASA and the scientific community, and for supporting basic research and education dealing with life in the universe, he was honored with NASA's Distinguished Public Service Medal. Tom was a leader and a friend to many. He was an athlete and a dedicated family man, played competitive golf in college, loved baseball and football, and shared his passion for sports with his son Tommy, daughter Elizabeth, and wife Elise. Tom is remembered as enthusiastic, generous, and fair. He dedicated himself and his career to what he called the most profound search in human history, to know our beginnings and our place among the stars. Tom is deeply missed.
Colin pioneered many studies on meteorites that advanced our understanding of how the solar system formed and the geological and geochemical evolution of planetary bodies. Colin was always a determined person, and after moving to the Open University, where he made professor of planetary sciences in 1991, he rapidly built up expertise not just in the scientific study of meteoritics, but also in instrumentation for examining organics on other planetary bodies such as mass spectrometry. These instruments would eventually fly to other planets and comets. With his signature sideburns, his West Country accent and flair, Colin was always a formidable and influential force in science. Colin's largest scale contribution to astrobiology was the implementation of the Beagle 2 lander, a lander designed to search for organics on Mars, measure their isotopic composition, and investigate the geology of the red planet. Beagle 2, which was launched with the European Mars Express mission, is thought to have successfully touched down on Mars, but it never made contact. Colin's enthusiastic personality and love of science did more than launch a spaceship. He was also instrumental in inspiring many people to go into science and in encouraging astrobiology and related areas of activity in the UK. The Beagle 2 mission was highly influential in improving public understanding of space missions, planetary science, and science in general in the UK, and did much to bring planetary sciences into the forefront of science.
The field of geomicrobiology lost a treasured and vibrant leader, champion, and friend on October 26, 2014, with the passing of Katrina Edwards. arguably the first person to attain a PhD in the field of geospatial biology. In 1999, at the University of Wisconsin, Katrina was well known for her trailblazing abilities and attitude. Going straight from her PhD to the rank of assistant scientist at Woods Hole Oceanographic Institution was remarkable enough, made more so by the fact that she had no oceanography experience at the time. Not one to be deterred by such challenges, Katrina quickly established herself as a major player in deep-sea research at hydrothermal vents, studying how microbes interact with ocean crust. She did this while simultaneously growing her family into 3 young girls. Transitioning to dual professorship in biological and earth sciences at the University of Southern California in 2006, Katrina went on to establish a $25 million science and technology center devoted to deep biosphere research in 2010, and to be co-chief of the International Ocean Drilling Expedition in 2011. Katrina was recognized for her contributions to scientific discovery with many awards, including the A.G. Huntsman Award for Excellence in Marine Science in 2012. Katrina will be remembered fondly by her close colleagues by her "Get Shit Done" motto, always said with a playful smile and laugh, and her spirit will live on in the next generation of intraterrestrial researchers hunting for microbes that rust the crust.
Martin Brazier was a leading paleobiologist from Oxford University, well known internationally for contributing to debates that influenced our understanding of the early biosphere and key points in its history. He was a recipient of the Geological Society of London's prestigious Lyell Award. During a more than 45-year career, Martin covered the entire geological timescale on all continents except Antarctica. For the last 15 years, he focused on the origins of early life during the Archean and the subsequent warm billion of the Proterozoic. Martin relished collaborating and contributing as a member of the scientific community that teased out of rocks the complex story of life. He recognized early on the necessity of multidisciplinarity in addressing questions raised through field mapping, microbiology, and geochemical analysis. He was never afraid to enlist the help of other experts. He frequently referred to the Archean early biosphere studies as his most satisfying research project, and his approach yielded a high scientific return in publications, the chronology of which reveal his changing position on the timing of the first life on planet Earth. Martin was also an accomplished piano player, enjoying jazz, and had the practical skills to restore and build his own keyboard. In his later years, he discovered an interest in historical microscopes and began assembling an impressive collection, including one that had belonged to the American micropaleontologist Joseph Cushman. A new generation of students can appreciate Martin's ability for storytelling in his popular science books, Darwin's Lost World and Secret Chamber, that will bring the Precambrian to life for a new and diverse audience. Martin tragically died in a car accident not far from his home in Insham, Oxfordshire, on the 16th of December, 2014. Thoughts and sympathy go out to his wife Cecilia, who is thankfully recovering from her injuries sustained in the accident, children Matthew, Alexander, and Zoe, and 2 grandchildren. Fortunately, he has left us with a rich and wide-ranging scientific legacy.
Alberto was a polar researcher who spent many summers on the Greenland ice sheet. Alberto was a professor at Arizona State University in the Grand School of Biology and Robotics. Alberto was an investigation scientist instrument on the Curiosity rover and Mars Odyssey orbiter. Alberto and I first met when we both started working for NASA's Jet Propulsion Laboratory. Alberto and I became colleagues and friends. Alberto was particularly on his job. Alberto loved music. Alberto was the first and the first. I would be a lifelong friend. Alberto always had good plans. And even though he was only 25 years old, Alberto had stick pins all over Asia and Europe, the Middle East, North and South America on that world map. I do not remember any marks in Africa or Antarctica, but those flags would soon be planted. Alberto has always been eager to meet new people, explore new lands, and imagine new ideas. One of his not-so-great ideas was taking in a dog named Genghis. He loved Genghis, even when Genghis ripped up all the carpet in our living room. His most infamous idea was to drop rubber ducks into a natural drain hole on the Greenland ice sheet to determine if meltwater from the surface reached the sea. His best idea by far was to marry his wife Mary and create 3 beautiful, smart, wonderful children. Alberto was passionate. Alberto was trained to hold a running. One time, everything was jumped into factory. Factory milk, factory flowers, factory every time.
Houston is go for docking. It's up to you guys. Have fun.
Alrighty, sounds good. Palavina Mila Alexei. Soyuz docking system is ready. Good job. Let's see that. Look at that. I am approaching Soyuz. Mom, please don't forget about your engine. Less than 5 meters distance. 3 meters. 1 meter. Contact. Capture. Tell Professor Bashuyev it was a soft docking. Well done, Tom. It was a good show. We are looking forward now to shaking hands with you in both of you. Alright, on a show. On for year with 3. Okay, the
As you moved outside of the Voskhod spacecraft, Pavel Belyayev, your crewmate, was watching very carefully. You wrote in an article for Air and Space magazine several years ago that you felt like a seagull with its wings outstretched, soaring high above the Earth. What was that experience like? It was a very short spacewalk, but you had great recollections.
The perception of space, the perception of environment. And what I saw, and I saw just half of the world, is we were 500 kilometers above the Earth. And nobody, even up until now, nobody is flying that high. So I saw a radius of half of the planet of Earth. And the ability to see the whole Earth as a globe, pretty much, is something that was extremely attractive. And I could easily recognize the Black Sea, the Crimea, Romania, Bulgaria, Italy, looking up a little bit, Baltic Sea, and it was all within minutes, if not seconds. But the most impression had to do symbolic representation of a seagull, although to me it's more like a paratrooper in a free flight. This analogy is closer to me personally. But once again, silence. These stars were very bright. There was a lot of them. And it was interesting that they were everywhere. They were above and they were beneath. And on the ground, we can only see stars up in the sky. In space, they are everywhere. And it depends on how good a vision of an individual is, but in space, we see much smaller stars.